Let us keep continuing with the VBT. Now, these are very important cases here, guys. So, when you have, let me write down that note here first. Okay. The note here is if nickel plus 4, okay, is the central metal atom, then all ligands, all ligands are strong field ligand. Because of such high positive charge, it will always show it like a strong field ligand for any kind of ligand, whether it is fluoride, chloride, iodine, anything. Similarly, cobalt plus 3 makes borderline borderline ligands, okay, like H2O, EDTA 4 minus, okay, oxalate 2 minus, as strong field ligands, correct? But these are generally weak fields, but when you connect it with cobalt plus 3, they will automatically become strong field. Other than that, any any 4D 5D, okay, any 4D 5D, or let me put it this way, okay, one second. So any four any fifth, or sorry, any 4D and 5D series elements, 5D series elements make, any 4D or 5D series elements make every ligand, every ligand as strong field ligand only. So for example, if you take platinum, palladium, rhodium, okay, ruthenium, osmium, any of these metals, if they are forming complexes, it is always regarded as strong field ligands. Whatever the ligand is, we'll always consider them as strong field ligands only. Okay. So keep these three fundamentals always clear, or these statements clear, so that the solving becomes easy. Now, come to this question here. For example, in this question, to find out the hybridization, number of unpaired electrons, what type of complex it is. So first we need to check out its primary valency. Primary valency of nickel in this case is 4, secondary valency is 6. Here primary valency is 3, secondary valency is 6. Primary valency is 3, secondary valency is 6 again. Why 6? Because it is a bidentate. Oxalate is bidentate. So, which means if we take the nickel configuration here, it is about nickel plus 4 configuration. Nickel plus 4 configuration implies we have argon 4 is 0 and 3d6. Here also we have cobalt plus 3 configuration will be argon 4 is 0 and 3d6. Here also cobalt plus 3 will have argon 4 is 0 and 3d6. Now, since nickel is at plus 4 oxidation state, it would make every ligand as a strong field only, which means the pairing is possible. So, due to strong field ligand, here also due to strong field ligand, here also this due to strong field ligand, there is pairing possible. So, if it is pairing possible, that means 3D orbital now, I have to put 6 electrons in a paired form. 1, 2, 3, 4, 5. Then we have 4s, then we have 4p, correct? This is 4s and 4p. I have to accommodate 6 electrons into it. So you can see 1, 2, 3, 4, 5, 6. Everything is paired. So after pairing, now you'll notice that these orbitals are empty, which are ready to hybridize. So as they hybridize, it will become D2sp3. Correct? So the pairing is possible. and we require two d orbitals. Either it is inner d or outer d. Since inner is available, we always use the inner d orbital. Hence we will get the hybridization as d2sp3 in all these three cases, correct? So this is d2sp3. And you see the number of unpaired electrons. Originally the number of unpaired electrons were only 4. Why? Because when it is 3d6, 3d6 normally will have electrons like this: 1 2 1 2 3 4. But now the number of unpaired electrons are 0. So number of unpaired electrons are 0, which makes it low spin complex. So this is a low spin complex and diamagnetic material. Okay. The same thing will be applicable even for this cobalt and even for this cobalt as well. Okay. And all of them are forming inner orbital, inner orbital octahedral complex. Inner orbital octahedral complex. Okay. Octahedral complex. Octahedral complex. Right. That's the same thing valid for the other two cases also. Okay. So guys, this is something which you need to, take it as an assumption for solving. Use these fundamentals and do these cases, and you'll get everything that is required. Please quickly notice that. If there is any doubt, you can ask me now. As long as cobalt plus 3 is concerned, if you have all fluorines, right, then it is weak field only. Overall, it is going to be weak field. So you consider this as weak field ligand. Since it is weak field ligand, you have to go for outer orbital complex only. So this will remain paramagnetic, and this will be uh, high spin complex. Okay, these are the terms you should know. Even with four fluorides also, it is still going to be, what about five fluorides? I didn't write down. Okay, sorry, let me write down that also. Cobalt with five fluorines and one water. Okay, that with -2. Even with this also, it is still going to be the same, weak field only, and all of this, correct? Even if you have four, still weak field. Even if you have three, it is weak field. Now when water will dominate, when water is more than fluorine, then this will become the above case. So it will be same as the above case, which is strong field ligand d2sp3. It is diamagnetic and it is low spin complex. Clear, everybody? So all these cases have been asked in JEE Advance, once in a while. So please learn that cobalt cases are very, very exceptional and important. If all water is there, definitely it is going to be strong field. If you have five water and one fluorine, still strong. Four water, two fluorine, still strong. But after that, three fluorine, three water, four fluorine, two water, five fluorine, one water, or all six fluorines. All these cases are weak field ligands. Clear? So in any of these cases asked, in JE there are no multiple. There is no questions that should be asked when you have multiple ligands in it. Okay, that is one weak, one strong. When you have it, is not usually asked, but especially in cobalt cases, all will be asked. So be aware of that. Okay. Sure. Next. Now let's try to dig more into four ligand systems. If you have four ligands, then what are the possible hybridization, and how do we identify unpaired electrons and all the magnetic properties? Here, so please check out. There are two hybridizations which can be expected, that is sp3 or dsp2. To to understand how the algorithm works in this case, let's take the nickel cases first. Nickel with chloride exists with 4 chlorine form, cyanide with 4 chlorine, and carbonyl with 4 chlorine form. Okay. So let's first put the primary and secondary valencies here, everybody. So the primary valency of nickel in this case is +2. Secondary valency is +4. Primary valency here is also +2. Secondary valency is 4. Primary valency in this case is 0 because carbonyl charge is 0 and secondary valency is 4. Okay. If you have such case here, see. So these are primary and secondary valencies here. Okay. Now notice this one. When it comes to nickel here, what is the oxidation state? +2. So how about this one? It is argon, 4s 0 and 3d 8. Okay. Which means its 4p is still empty. Okay. Now, since we are dealing with a weak field ligand, since we are dealing with weak field, chloride is a weak field ligand, so there is no purpose of pairing here. So 3d would remain the same. So this 3d orbital would have all of those 8 electrons like this. Okay, sorry, here and here. 4s would remain empty. 4p is empty as it is. Okay. So we have no other option but to go for 4s and 4p only. That makes it sp3 hybridization. If it is sp3 hybridization, what is the hybridization? It is tetrahedral. sp3 and it is tetrahedral. Okay. So it is tetrahedral structure here. And what is the other thing which we need to learn here is we are using an uh, outer orbitals. Okay. And between low spin and high spin, if you say there is no change in number of unpaired electrons. So this is a high spin complex, high spin complex. And it is paramagnetic in nature because number of unpaired electrons are 2 in this case. Okay. This is the information you need to gather for nickel Cl4. See the next one, it is cyanide. So up to this form, I'll write everything same here. So let me just copy this part here. Got it. And now notice something. Now you are dealing with a strong field ligand. Now since we are dealing with a strong field ligand, okay, is pairing possible? Absolutely. Why pairing is essential now? Now listen up. I had two options to make four ligands to approach. Either it can go for sp3 or dsp2. Preferred form preference is always dsp2 first. Only if it is unavailable, then we go for sp3. Now, fortunately, in this case, after pairing the 8 electrons, we will get one unpaired electron completely. So, therefore, 1, 2, 3, 4, 5, 6, 7, 8. I mean, one empty orbital. So, this one empty orbital is identified. So, I can use that and then go this way. So, what do I get? dsp2. That is what we will have. We will get this as dsp2. Okay. Which makes it dsp2 is a square planar case. So, this is a square planar geometry and now the number of unpaired electrons has decreased. That makes it as low spin complex. This is a low spin complex. As number of unpaired electrons now it has become 0 and also it is a diamagnetic complex now. This is diamagnetic. It has used an inner d orbital. That's why it is also called as inner orbital complex. It is an inner orbital complex. Got it? I hope this part is clear, everybody. Please do check quickly about these two cases. Let's see this last case now. Again, let me copy this part. Check this out, something important here. This is carbonyl is a very strong field ligand. Even though it is a very strong field ligand, the nickel's oxidation state is 0 here. which means we have electrons in 4s. So we have basically 4s2 and 3d8 and 4p is empty. Now, what would happen here is there are electrons present in 4s also, and there are electrons present in 3d also. So this is the condition right now. Original condition is like this. Okay. Since this is an original condition here, correct? Now what would happen? As soon as the strong field ligands approach, as soon as the strong field ligand approach, 4s electron will also get migrated, everybody. Okay. So how does it migrate? 4s will start migrating one electron here and one electron here. This is the kind of migration that is going to happen. Okay. So once the migration completes, now there will not be any electrons in 4s. So all of the electrons will now get into 3d. So 3d is completely unavailable and it will become d10. Originally it was 3d8 and 4s2 and 4p 0. Now 4s will become 0, 4p will become 0 and 3d will become 10. Okay. That makes it there is only availability of, sp3 hybridized orbital. So hence it is going to be tetrahedral geometry and rest of all features will be similar. So this is going to be low spin complex. It is going to be diamagnetic because there are no unpaired electrons. Correct. And it is an outer orbital because it is not using any. So we do not use the word outer orbital also because we have not used D at all. So it is simply sp3 or hybridized orbital. Clear? So please notice these three cases quickly. Usually most students have doubts in cobalt cases. So please check out cobalt cases thoroughly. Finished? Right. Now let's go into more four ligand cases here. Another set of example is about copper and zinc complexes. Let's go through it one by one. Let's put the primary valency. Everybody, please work out along with me. What is the primary valency, everyone? This is 2. Secondary valency is 4. Here also primary valency is 2. Secondary valency is 4. Primary valence is 2, secondary valence is 4. Correct? What shall happen here? See, primary valency is 2, which means it is cobalt plus 2. Cobalt plus 2 oxidation state goes like this: argon 4s0 and 3d9. That is the configuration. Here also, cobalt 2 plus will have argon 4s0 and 3d9. While zinc 2 plus has configuration argon 4s0 and 3d10. This is the configuration. Okay. Since chloride is a weak field ligand, so you cannot expect any pairing to happen. So hence we would have 3D where 9 electrons would be present as it is. Okay. Then we have 4s which is empty, and then we have 4p which is empty. So this is 4s and then this is 4p and 3D. So of course we can't find any alternative, so we have to go for sp3 hybridization only here. So that makes it a tetrahedral geometry. Okay. Hence, what we can say here, this is a uh, neither low spin nor high spin, neither low nor high, because even if you take strong field also, you will still have an unpaired electron. Got it? Second, it is remaining paramagnetic. It will remain paramagnetic for simple reason it has one unpaired electron, and hybridization will be sp3, right? So this is the idea we should have for cobalt in the first case. In the second case, now this time we are dealing with a strong field ligand. Since it is a strong field ligand, what do we expect here? In the case of strong field ligand, what do we have here is like, there are 9 electrons here. So this is 3D, 4s, 4p. Okay. Okay. So in that case, what has been noticed, right? Because the ammonia is a strong field, it will have the ability to even push the electrons all the way from this unpaired electron to this last orbit. What is the advantage in doing that? On doing that, what do we get here is we will get this 3D here. Second. Sorry. Check out. We have then 4s, 4p here. So now after that electron completely moving to the 4p orbital, now you can see these four will get hybridized and this electron will be appearing here. So what do I get? I'll get this as dsp2 hybridization, and dsp2 will be square planar in geometry. So this will remain square planar and it is going to be still paramagnetic. Paramagnetic. Why? The unpaired electron is still there, but paramagnetic, and unpaired electron is found in which orbital? Unpaired electron is found in 4p orbital. Is found in 4p orbital. So this is the idea which you need to collect from strong fields now. So strong fields in a way push that electron, that single electron to the outermost orbital so that it can get a hybridization of dsp2. Got it? Next, on the other hand, if you notice for uh, zinc case here, zinc case is a very straightforward one. It is a strong field, correct? But there are 10 electrons here. Since 3D is completely filled, there is no need or anything to disturb 3D. So simply we have to rely on 4s and 4p. So that makes it sp3. It is tetrahedral, correct? And it is again not a high spin or a low spin, because whether you take strong field or a weak field, this is the only hybridization that it will show. It will remain diamagnetic material, diamagnetic complex. Done. So please check these cases quickly, everybody. So in case of four ligands, I hope now you know how to make sure that you should look out for hybridization. Either it should be DsP2 or it should be sp3. Right. So this I told you already. If the central metal atom is coming from 4D or 5D, every ligand is strong field. So let's see this case here now. Okay. So what do we have? If we have primary valency is 2, secondary valency is 4 in the platinum case. Uh, Platinum is basically coming from uh, sixth period. Okay. Awesome. Check out, it is coming from the sixth period element. So therefore it will have xenon, correct? And then uh, 6s0, 6s2, and 5p, 5d8. That is its configuration. Okay, platinum's original configuration. Now if it becomes platinum 2 plus, so that will become, right, xenon, correct, 6s0 and 5d8. This is the configuration. So which means that the chloride which you are using is a strong field ligand. Since it is a strong field ligand, so we can say that the pairing is possible, right? So 5d will have 1 2 3 4 5. Here these will be paired up. 4s would remain empty and 4p will remain empty. So we could directly use this as D and S and P here, makes it into DsP2 hybridization. Okay. So since it is DsP2 hybridization, so you can say this is going to be square, square planar. This is going to be square planar, and it is diamagnetic, diamagnetic material, and it is using inner d orbital. So it is inner orbital complex, and also it is making it into a low spin form. So it is low spin complex as well. Clear? So fundamentally, wherever you have 4D and 5D, just use this logic that everything is strong field ligand, and you will be able to fetch it out. What should be the answer in this case? I guess this part is clear, everyone. Okay, done. Right. I have given you the list of cases where they could be either sp3, dsp2, or sp3d or dsp3, correct? And what are all those cases, and respective what are the examples in this case? Got it? Based on that, I would want you to check out all these cases once, should be able to answer them. And last few cases, right? Which one? This one I have discussed already. Okay. So this one I told you how do we need to think in terms of water molecule and fluorine are present in it. Got it? And other than that, the last one is what I will discuss 42 one. Please check this out. In the case of 42 one, there are two cases here. I mean, two different forms here. Chlorines are weak field ligand, while triphenyl phosphine are strong field ligand. In such case, how do we need to check that overall it is going to be strong field or weak field? So primary valence is 2, secondary valence is 4. So that makes it nickel plus 2 configuration, which is going to be 4s0 and 3d8. Correct? Now, if you notice this molecule, I mean the entire ligands all together as weak field ligand, then it is going to be sp3. If we perceive this as all the ligands together, averaging them, if it becomes strong field ligand, it is going to be dsp2. Okay. If it is weak field ligand, it is going to be nickel with four groups like this. We have chlorine, chlorine, PPH thrice, and PPH thrice. While if it is square planar, we will have square planar like this. So we can have two chlorines here and two PPH thrice and PPH thrice. So in fact, both of them are interchangeable. That means it will always go between uh, square planar to tetrahedral. So what I can say is the square planar geometry, which is DSP2, is in equilibrium with, okay, is in equilibrium with, okay, tetrahedral form. So tetrahedral form is sp3. Correct? Usually, the dominancy depends upon temperature. At low temperature, square planar is more observed. At high temperature, tetrahedral is more observed. Okay. So low temperature and high temperature varies this way, everybody. So in this case, please remember that both are possible. You just need to differentiate based on temperature. Okay. So check this out and write it down, everybody. Then everybody. The next concept from coordination compounds, right? The next concept from coordination compounds is about CFT, crystal field theory. All right. So let's focus on this part here now. What is crystal field theory? What does it do? One second. See, according to crystal field theory, correct? What we assume here is the interaction between the metal and the ligand, which is happening, is purely electrostatic. Okay. So you're expecting that the reaction is completely, the bond is purely electrostatic, which means ionic bond. Central metal atom is considered as a positively charged species, and the ligands are considered as negatively charged species. Now, in case of neutral ligands, negative dipole interaction with positive charge of the CMA is happening. So, for example, here the dipole, which is negative dipole, will make a positive interaction. Will make an interaction with the positive charge of the CMA. Next, there is spherical positive charge present, which balanced by the negative charge of the metal electrons. Got it? So, which means whatever the positive charge which is present on the metal, correct, we can assume that it is spherically spread, and that is being balanced by the negative charge of the metal electrons present inside. Got it? This is a basic assumption. What does that mean? For example, if you have a nucleus here, positive charge, and this positive charge is spreading some field around it like this spherically. Okay. And this spherical charge is being balanced by the electrons present in the outer shell or inner shell, everything, correct? Like this. So that will carry the negative charge. So that's how the metal will be balanced here. But the minutes when the ligand approaches, correct? When the ligands will approach, we expect that ligands are always considered as some negative charges, and they will mainly try to attract the metal's nucleus. Got it? They'll try to attract the metal's nucleus. And of course, what would happen here is while they are trying to attract here, they will cause repulsions with the electrons also. Correct. So that means these electrons get repelled by approaching ligands. They will get repelled by the approaching ligands. Okay. So, due to these repulsions from the ligands, the surface electron will observe to have more energy, or they increase their energy, correct? Or I can say their potential energy is increased. If d orbital at the outer surface, usually metal's outermost orbital is d orbital, and if the outermost d orbital, have an increased amount of energy. Originally, d orbital, all the five orbitals are degenerate. Degenerate means all of them have same energy. But after the ligand's approach, suddenly the energy of all the orbitals rises because of the repulsion. Now, while rising, not every orbital might get same amount of repulsion. Some of might get more repulsion, some of might get less repulsion. Because of which, there is a chance that the degeneracy is completely lost. In fact, in most cases, the degeneracy will be lost and it will split into set of new orbitals now. So that means from here onwards, it will start again splitting into set of two new orbitals like this, or in different way. This is one example. This is the way it will split, which means the total energy which is being raised in all the five orbitals is redistributed into set of three orbitals and set of two orbitals. So this loss of degeneracy is observed whenever we have ligands approaching to central metal atom. Now, we will learn this case by case. First case is about 6 ligand system. That means what happens and how the degeneracy is lost when 6 ligands are approaching. So notice this, when 6 ligands are there, if this is a central metal atom, and then ligands are approaching from all 6 directions here like this. Okay. So you can see that along x-axis and minus x-axis, y-axis and minus y-axis, and z-axis and minus z-axis, we can expect that all 6 ligands are approaching, because that is the best symmetrical way of approaching towards metal. So imagine if all 6 ligands are approached towards metal this way, then what I could say, that the orbitals, d orbitals, which are aligned across the, along the axis we have some orbitals, right? If those orbitals are being repelled by ligands, their potential energy will raise to a larger extent. That's the reason why you notice that dx square minus y square and dz square, both of these orbitals are along the axis. So they get most affected. That means they get more repulsion. While the other orbital, see this one, this orbital you can see, this orbital is basically dxy, okay? While this orbital is dz square, while this orbital is dx square minus y square. Now you can see that dxy is not actually coming head on with the ligand. Ligand is somewhere, orbital is somewhere like this. Correct? So it is not exactly coming head on. Hence, it will experience less amount of repulsions. Therefore, dxy, dyz, dxz, they will have lesser repulsions. Got it? And these three will have a similar degeneracy, while these two will have similar degeneracy. So, which means the overall increase in the energy of d orbitals as the ligands approach, that is, this much amount of energy has increased. Let's say delta naught is ideally the amount of energy that has increased. And that energy will be redistributed into set of new orbitals. The lower energy set, which is made out of dxy, dyz, and dxz, they are called as T2G orbital, T2G set, and higher orbitals, higher energy orbital, which is dx square minus y square and dz square. This as a total set is called as EG. Okay. How much? See, out of 5 here, there is a loss which has been given, loss of energy which has been given out by these two orbitals. So therefore, it is minus 2 by 5 delta naught loss in the energy, and above these three, whatever energy they have, that we have distributed it to these two. So that means each orbital has a gain of 3 by 5 delta naught of energy. So this much amount of energy is raised above and this much amount of energy is raised below. The central energy line is called as barycenter. This is called barycenter. So after the bond formation, usually this is the situation we will have. And see this, the delta naught that we are talking about, that is called as splitting energy or shielding energy. This is called splitting energy or shielding energy, everybody. Clear? Notice this. Suppose if these 5 electrons were present, imagine there are 5 electrons present in d orbital originally, okay, before the ligands approach. But after the ligands has approached, after the ligands has approached, what will happen to the situation? After ligands has approached, there are two situations we can have. One, following Hund's rule, we will first fill the T2G orbital or T2G set. So you'll get 1, 2, 3, and then follow to EG, higher orbital, which is 1 and 2. This is one way of filling. The other way is either you fill all 5 electrons here only, 1, 2, 3, 4, 5. So this is like following Aufbau's rule. Okay. Here it is only following Hund's rule, but not following Aufbau's rule. According to Aufbau's rule, the lower energy orbital should be completely filled before we go to the higher energy orbital. But that's what not we are doing here. Now, in which case this will happen? Listen, if the splitting energy is large, if the splitting energy is large, then it is difficult for the fourth electron to go here. That's the reason why it is following Aufbau's rule and getting paired in T2G only. But if the delta G naught value is smaller, that means there is not a large splitting of energy here, then that usually happens with a weak field ligands. And this time the fourth electron will go to the higher orbit by violating the Aufbau's rule. Okay. Now, how and when the Aufbau's rule is violated here? See, check out. Whenever you are pairing an electron, see, electron is present in an orbit. If you bring a second electron onto it, got it? then these two electrons will have some repulsions. So that means there is some energy required to keep the electron there. That means to pair the electron. The energy required to pair the electron in a particular orbital is called as pairing energy. Now listen, if the pairing energy of every orbital, if that is greater than delta naught, if that is greater than delta naught, in that case the excitation, that means the fourth electron will go here. That usually happens when pairing energy is greater than splitting energy. But if splitting energy, if splitting energy is greater than pairing energy, then the gap will be larger. So the fourth electron will not choose to go to the higher orbit. Rather, it will start pairing because pairing energy is less required. Correct? And released energy, which is the splitting energy, is more. So why would it go higher orbital? Overall, our idea is to keep the energy as low as possible. That's the reason when you take strong field ligand, delta naught will be greater than pairing energy. When you take the weak field ligand, delta naught will be less than pairing energy. So in the cases like ammonia, ethylene diamine, carbonyl, cyanide, PPH3, these are all strong field ligands. Halogens, OH minus, O2 minus, oxalate, S2O3 minus, S2 minus, H2O, these are all going to be weak field ligands. So in the case of weak field ligands, you will see the pairing energy is more than delta naught. Okay. Now consider this. Total energy of the complexes after the ligand makes a bond is called as CFSE. That is crystal field splitting energy. This is the total energy of the complex. By formula, how do we write down? See, here you can see when you have a splitting here, correct? So we have T2G set as well as EG set. T2G and EG set. This is EG and this is T2G. Okay, clear? And from this Barry's center, we know that the decrement in the energy is minus minus 2 by 5 times of delta naught, while here the increment in the energy is plus 3 by 5 times of delta naught. So that's what I have taken it here. In this case, how many number of unpaired electrons are present, or total number of electrons are present? That is called N-T2G. That means number of electrons in T2G. That multiplied by this energy factor plus how many electrons are present in EG. That multiplied by 3 by 5 into delta naught factor. Okay. So multiplication of these two plus how much is the pairing that has been done. Is there any pairing that has been done? That will be new number of pairs. Here n represents new pairs. N is new pairs. How many new pairs are there? That into pairing energy. So this represents the CFSE value. Generally, CFSE value is always negative, and higher the negative value, more stable the complex is. Okay, so that's how we will always judge the stability on the basis of CFSE value. So 2 by 5 is 0.4, 3 by 5 is 0.6. So this turns out to be the formula. So I hope theoretically, I hope all of you understood what is CFSE, why the splitting happens, after splitting happens, how the degeneracy is lost, and in which case we have to do the pairing or we have to just excite the electrons. Okay. So now notice this one. This is a table. We'll have to do it together, everybody. So let's check it out. If it is a strong field ligand, how do we pair it? So check out. If it is only D1, first electron is entering into the new set of complex after the ligand's approach. Then T2G will have only one electron. EG will have 0 electrons. Here also T2G will have 2 electrons, EG 0 because we still did not get into EG. So T2G 3, EG 0. T2G 4, EG 0. T2G 5 and EG still 0. T2G 6 and EG still 0. Okay. Eg is still 0. Here also Eg is still 0. Up to this, you can notice because it is a strong field, it has completely filled the T2G. And only after filling T2G, that is when it will enter into Eg. So now it will go to Eg1, then T2G6, Eg2, T2G6, Eg3, and T2G6, Eg4. So that's how the pairing happens, everybody. Got it? So T2G1, number of unpaired electron is 1. Here number of unpaired electron is 2, then 3. After that, the number of electrons again decreases 2, then 1. In this case, it is 0. Again, we have 1 and 2. Here we have 1 and 0. These are the number of unpaired electrons. Got it? Right? You know the number of unpaired electrons. Now let's calculate the CFSE value. CFSE value, in the first case, I'll calculate. Rest all the cases, you can directly do it. Check out how much it will be. First case, we have minus 1 into 0.4 into delta naught plus Eg is 0, okay, into 0.6 into delta naught, this entire thing, plus there are 0 pairing electrons, new pairs have not formed, so 0 into pairing energy. This will be the CFSE value. Hence, the answer would be, CFSE value will be minus 0.4 delta naught. Like that, if you do for the next one, it is minus 0.8 delta naught. Next one, 3 unpaired electrons, so minus 1.2. Then we'll have minus 1.6 delta naught, minus 2.0 delta naught, minus 2.4 delta naught. Then all 6 electrons have been done. Now when it comes to 7th electron, now it will be minus 2.4 delta naught, minus 2.4 delta naught, plus 0.6 delta naught. Okay. So that makes it, you know, that makes it how much? Minus 1.8 delta naught. Okay. Next one will be minus 1.2 delta naught, minus 0.6 delta naught, and lastly 0. Okay. So you'll get only one case where the CFSE is 0, that is D10 configuration. The highest value you will find is, is for D6 configuration. That's very, very important. So when you have a strong field ligand in a 6 ligand system, then D6 is the most stable configuration form. I think now you can relate that why nickel cases, cobalt plus 3 cases, they are showing exceptionally high strong field nature. Okay. I told you that cobalt plus 3 is making a borderline ligands like water, oxalate also into strong field. Now I think you can relate it. Why it is making them strong field? Just to attain the D6 configuration from a strong field's point of view. So if it becomes a strong field, huge amount of energy can be released through the molecule and the complex can become stable. Okay. Now coming to the pairing energy. Notice one thing. In the first case, originally when you have the configuration, so let me write the original configuration here. So when it is D1, all 5 orbitals, I'll put it 1, 2, 3, 4, 5 orbitals here. Okay. So let me rewrite that. Yeah. So these are 5 orbitals. I'll just copy and put it to Even if you do not write this, that is okay. This is just for your reference. Please check it out. First, there is only one unpaired electron, which is here. Second one is here. Third one, generally we fill like this. Fourth one, we fill it like this. Fifth one, we fill it like this. Correct? Sixth one, we'll fill it 1, 2, 3, 4, 5, 6. Seventh one, this is how we'll do the filling. Eighth one, you know that we have 3 pairs and 2 unpaired electrons. Ninth one, we have it like this. Okay. Now, in the case of T2G, see, T2G, we have three set of orbitals, and EG, we have two set of orbitals, correct? This is what we have. Okay. Now, let me copy that and put it for all the cases here. One second, I'll remove this part. So, please notice this one. So, here also, I'm putting one electron here. So, first electron goes here, second electron goes here, third electron goes here, fourth electron, please check it out. There is a new pair. Please compare carefully, everybody. Originally, there was no pair, but now there is a new pair, correct? So that's when you add plus 1 into pairing energy. Okay. Now see the fifth one. You have 1, 2, 3, 4, 5. So originally there is no pair of electrons. Now they got two pairs. So 2 into pairing energy. Correct? 6. We have 1, 2, 3, 4, 5, 6. Originally there was already one pair. Now we got two different pairs, two new pairs. That's why you will be adding two times of pairing energy only, not three times. That's a usual mistake kids do. So no, you need to check out how many new uh, pairs have formed after the complex formation. Now, from here onwards, you will not have any change in the number of pairs. So you can see originally we have six pairs, correct? Six pairs here. So one electron coming here. So that means only one extra pair has been developed, correct? Eighth onwards, you will see this number of pairs are same. This is the configuration. So no pairing. Ninth also, we will have four pairs before and four pairs after. Fifth, here we had all the electrons. Here also we have all the pairs same, exactly pairs same. So therefore you will not have anything. So pairing energy comes into picture only between D4 to D7. Okay. Sorry, please check. Make sure that you got an idea about how to represent the strong field again, or how to represent the CFSE value. Okay. Number of unpaired electrons you can know from here. So we can easily calculate the magnetic moment. Mu is the magnetic moment, correct? So if you have one unpaired electrons, the formula is under root of n into n plus 2 Bohr magnetons, Bm, right? So n into n plus 2 means how much will be the mu value? Here it will be root 3. Here it will be root 8. Here it will be root 15 Bohr magnetons. Here it will be root 8. Here it will be root 3. Here it will be 0. Here it will be root 3 again, root 8 again, root 3 again, and 0 again. This is the mu value. If you have any doubt, please do ask. In case of weak field ligand, how will be the uh, CFSE value and all of this would vary. Okay, so I'll do one thing. I'll directly copy everything that we have done here and see how it goes on this case. See which all things will be matching and which all things will not match here. Okay. See, the weak field and strong field distinction specifically comes when it starts from D4 only, correct? Otherwise, it is not coming at all. So, therefore, pairing energy will never be the factor at all in this case. That is the first thing you need to understand. So, there is no factor like pairing energy that will come into picture, correct? And the first three cases will be exactly same whether it is strong field or a weak field. Okay. Problem starts with fourth case. In the fourth case, when it comes to EG, now the EG electron will change. Okay. Here T2G and EG electrons will change up to which one? Only up to D, only up to D7 that will change. So how does that change? Check. After T2, after this, now you will get one electron here, correct? And one electron will go here like this way. And same way here also, you will notice that between these two, you have one, and two electrons here, this way. And in the case of this, you'll get one, 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 and fourth one, and this way. And last one here. And next we have 5 and 6 here, done. So 7 here, this is the case. And 8th onwards, it will be exactly same. So what is the distribution here? So we will see this as 4, 1, 4, 2, 5, 2, and 6, 2. Okay. 6, 2. And here you will have, sorry, 5, 2. My mistake, sorry, 3, 3, 1. 3, 2, and 4, 2, 5, 2, and 6, 2. That's it. This is a configuration change, what you will notice. So only change that is observed is from 4 to 7. Clear? Right. So based on this, now you see how much will be the number of unpaired electrons, everybody. So the number of unpaired electron part will change from 4 to 7. So this I'll change it. So what will be the number of unpaired electrons in this case? You will have 4 unpaired electrons, then 5 unpaired electrons, then again 4, then 3. Okay. So 4 to 7, I have to change these values as well. Got it? CFSE value will change now between 4 to 7. 4 to 7, the value will change. Let's see. Let's calculate that CFSE value now. So, for example, here we have 3 electrons in T2G and 1 electron in EG. So that means minus 3 into 0. Uh, 0.4 plus, okay, minus 3 into 0.4 plus 1 into 0.6. So that into delta naught. Okay. That will be equal to minus 1.2 delta naught. Okay. Right. Sorry, 1 second. Why would that be minus 1.2? 3, sorry, minus 0.6. Minus 0.6 delta naught. The next one, if you compare, it will be another 0.6 to be added here. So that makes it 0. And then you'll have one extra here, minus 4 into 0.4 plus 2 into 0.6 delta naught. So that will be equal to 16 minus 12, so minus 0.4 delta naught. And here you'll have minus 5 into 0.4 plus 2 into 0.6. So that is 2 minus 1.2. So that means minus 0.8 delta naught. That's it. These are the values. You will have something different. Now, since you have 4 unpaired electrons, so root 24 will be the Bohr magneton here. 5 unpaired electrons, so root 35 Bohr magneton. Again, root 24 Bohr magneton. And here we have root 15 Bohr magnetons. Okay. So please check this order, everybody. So when it comes to weak field ligand, this is the values of CFSC and unpaired electron. Now, what you need to notice here is that CFSC becomes 0 at 2 points here. So when you get D5 configuration and the other one when you have D10. Of course, D10 is a common one for strong field or a weak field. So what does it mean is that a weak field ligand making with a D5 configuration complexes are not very stable. Okay. So manganese plus 2, just think about it. If you have manganese plus 2 complex, right, with a weak field like water, MnH2O6 2 plus, those kind of complex, of course, complex will form, but in comparison to other complexes, it is not very stable complex. Clear? So this is an important part. We need to understand how to calculate the CFSC, right? Both in strong field as well as weak field cases. Okay. This explains the same fact which I'm trying to tell you, that why chromium plus 3 is more stable than Cr plus 2 and manganese plus 2 is more stable than Mn plus 3. Okay. So notice this one. In case of chromium plus 3 complexes, which means especially we are talking about aqueous solution. Aqueous solution means chromium is H2O 6 times plus 3. And when you have manganese plus 2 aqueous, which means manganese would always exhibit as MnH2O6 plus 2. Okay. In such case, chromium plus 3, the because chromium plus 3 configuration is 4s0 and 3d3. 3d3 configuration for a weak field ligand, it does not make any difference because weak field or a strong field, T2G will be filled first and EG will be left over. Okay. So in the case of manganese here, when you will have 4s0 and 3d5 here, correct? You would notice 1, 2, 3, 4, 5. Okay. So there is one nature that we will get. When all the orbitals are filled with one electron, we say it is half filled stability, correct? So this is T2G and this is EG. Okay. In case of chromium plus 3, we explain the stability on the basis of T2G. Half filled, half filled T2G makes Cr plus 3 more stable than Cr plus 2. While here, when it comes to manganese, half filled, half filled T2G and Eg makes Mn plus 2 more stable than Mn plus 3. Got it? So in one case, plus 3 is more stable. The other case, plus 2 is more stable. Got it? Now, you might counter argue the fact that, but the CFSC value is not very good here, or the CFSC value in this case, here it can explain based on CFSC, but here we cannot explain much on the basis of CFSC. Yes, here it is not just the CFSC value which we have to consider. We have to look into the case that how the half-fill stability is. Generally, Mn plus 2 complexes or Mn plus 2 salts are more stable because they attain that half-fill stability in uh, d orbital. Okay. But in this case, I can definitely explain that on the basis of CFSE, that T2G will have more electrons. If one more electron goes here, that will decrease the CFSE value, and that half fill stability of T2G makes it more stable. Got it? So I suppose this part is clear, everyone, right? Done. Okay. So we'll stop it here for today.